here we are going to see Gauss law for electricity and magnetism. We will begin with the Gauss law for electricity. First, let's remind the concept of flow. Flow is volume per second. So the units are cubic meter per second or other unit of time. If we have here, let's say, a tube, here the flow is some, let's say, 5 cubic meters per second, or I could say 5 cubic decimeter or 5 liters per second or whatever. Here I have the same as volume is area times distance, and I am dividing this by time or by second, minute, whatever. So this is the same as volume per time, but this time distance divided by time is the same as the velocity. So this part is velocity, and so I have that the area, the cross-sectional area of this, so area times the velocity is equal to the volume per time, or the same as flow. So I could say that the flow, that is the area times the velocity, is 5 cubic meters per second. This is if the water or the fluid that we have is going in this direction, that is exactly perpendicular to the cross-sectional area, so like this, like this, like this. Now if I have that this cross-sectional area, I will put it here is just this part, and here is the flow. If this cross-sectional area instead of being something like this, I put it with some inclination, let's say with this inclination. Now the flow will not be just the cross-sectional area times the velocity of the fluid, because not all this fluid is passing through this area, because now the area is not perpendicular, the area has this inclination. So it would be only the component that is perpendicular to the cross-sectional area would be the fluid that would be passing. So it would be the fluid that has contribution to the flow. That would be just the cross-sectional area times the velocity, the component of the velocity that is perpendicular to the cross-sectional area. So that is perpendicular to the cross-sectional area. Now we can introduce something that is called the area vector. This area vector is a vector in which the direction is perpendicular to the area that we're talking. For example, this is the cross-sectional area, so this is the direction of the vector area. If I have that this is the cross-sectional area, this will be the direction. So the area vector has the direction that is normal to the surface, and the magnitude is the magnitude of the cross-sectional area. For example, here I could say that the cross-sectional area are 5 square meters, and the velocity, in the case of having the area like this and the fluid coming in this direction, let's say that the velocity is 1 meter per second, so I would have that the flow is 5 cubic meters per second. So I could write the flow like flow is equal to area dot product velocity, vector and vector. Here, because now the area, I'm talking about the area vector that has the direction perpendicular to the surface. So I'm talking about this. This is the area vector in this direction, and the velocity is also in this direction. So when I have that the area vector and the velocity vector are in the same plane, so that the angle is the same, let's say 0 or is 180 degrees, so the cosine of 0 or the cosine of 180 degrees would be, for this would be -1 and this would be 1. So when I have that the surface is perpendicular, the cross-sectional area is perpendicular to the flow of the fluid, I have that the flow is just the area times the velocity, or that is just the vector area times the velocity, because area vector times velocity vector is area, the magnitude of the area times the magnitude of the velocity times the cosine of the angle between them. If the angle is 0, all the flow is passing, or all the fluid is passing through the surface, so I would have that is just the area times the velocity, that is what I have here, when the area is perpendicular to the cross-sectional area is perpendicular to the flow of the fluid. Now when I have the inclination, I was talking like, for example, this inclination, the flow is not in this direction, the flow is in this direction. So I'm just care about the component that is perpendicular to the cross-sectional area, or the component that is parallel to the area vector, because the area vector is normal or perpendicular to the cross-sectional area. So this is just to say that when I have the inclination, here I have the let's say this is the vertical line, and instead of having just like this is the vertical that goes here. I have some inclination, let's say this inclination. So the flow is going in this direction, So I have all this is the flow. So I could put this line. I know that this angle is the angle that makes the area or the surface with the perpendicular line. This angle I will call it theta. So this angle is 90 minus theta. Here, this is the opposite angle, so it's the same. This is the same. Here I have the normal vector to the surface. This is the normal vector. I could put it here. This is the normal vector. So all this is 90 degrees. So just this part could be 90 minus theta, so would be just theta. And so I have that this, if I put it again clean, this is the surface, this is the normal vector, and this is the flow direction of the fluid. So I have that the flow is equal to just the area vector, that is this is the area vector normal to the surface, dot the velocity vector, because it would be the magnitude of the area times the magnitude of the velocity times the cosine of the angle that is between them. And I could say the cosine of this angle or the cosine of this angle is exactly the same. So now this is flow. Now if we replace velocity times the electric field E, that in Coulomb's law we have the force is equal to Coulomb constant times Q1 times Q2 divided by the distance square. The electric field is just the force divided by the visitant charge, that would be Q2. So it's just K times Q1 divided by square R. This is the electric field. So now if I replace electric field with velocity, I have something called not flow but flux. So flux, and it's denoted by P. Sometimes you can put a sub E here. This is equal to E dot, or the electric vector, electric field vector times the area vector. This is the flux. Now how can we know what is the electric flux of something? Let's say that we have a sphere. This is the simplest one, this sphere. For this we need some symmetrical arguments. The symmetrical shapes that are most commonly used in Gauss law are spherical, that is the one that we will review here, cylindrical, and planar. So here I have, could be whatever, a charge Q1, and I want to know what is the flow, the electric flux here at this point. So what I would do is I would put a Gaussian sphere, that is just, or a Gaussian surface is just the imaginary surface, and I say that all the flux that passes through here, through all this sphere, so the flux, all this flux would be equal to, here I have the electric field times the area. So I have electric field times what is the area of the sphere, that is 4 pi r square. So the electric field, well, this would be the flux at this point, but if, well, the same as at this point, or well, the flux through this sphere, or I could say the electric flux through this sphere, and so I would need to calculate the area of this new sphere and the electric field that would be the same here as here, or the electric field of here would be the same. But if I don't want to know the flux, if let's say that I know the flux and I want to know the electric field at this point, what I could do is I will divide the electric flux by the area of the Gaussian surface. In this case, it would be 4 pi r squared, and this would be equal to the electric field. And this is the trick that we use, the Gaussian surface in Gauss law to calculate the electric field. So in this case, we would have that the electric field is just the flux divided by the area. So for a sphere, we would have the area is this is the electric field. For a sphere, the flux would be, flux is electric field, that is Coulomb's constant times Q1 divided by the radius square times the area, that is 4 pi r squared. So I have that the electric flux is just Coulomb constant times Q1 times 4 pi, and I kill this r squared. Now Coulomb constant is the same as 1 over 4 pi epsilon naught. So I can substitute it here, and I would have that the electric flux is equal to 1 over 4 pi e squared q1 times 4p. So I kill the 4 and p, and I have that the flux is equal to q1 divided by epsilon naught. That means that the flux through this surface, wherever this sphere or this sphere, is just the charge that is inside divided by epsilon naught. It could be different. For example, here I have just this. So the flux through this sphere is exactly the same as the flux through this sphere. If I had, let's say, some Q here and some other Q here, then the electric flux through this sphere would be just the Q1, actually this is Q inside. What is the Q inside is just this Q1 divided by epsilon naught. But the flux through this second sphere would be Q inside is Q1 plus Q2 divided by epsilon naught. And so I have that the flux is equal to the electric field times the dot the area vector, and this is also equal to the charge inside divided by epsilon naught. So I could say that the area, because I could take just the flux through this infinitesimal area, is just, here I would say the flux of infinitesimal is equal to the electric field dot dA. So if I want the flux through all the surface, would be the flux is equal to the integral. Actually it is the integral of a closed surface, and actually it is a double integral, but because here you're putting dot dA, you can just put one symbol of integral, and because it is a closed surface, you put this, and so the electric field dot dA, this is equal to Q inside divided by epsilon naught, and the electric field could be constant here at any point, so you could just say electric field times the integral of 1 dA, or well, dot this, is equal to Q inside divided by epsilon naught. So you have in dot A is equal to Q inside divided by epsilon naught. Now here, if you see, the electric field is perpendicular to the surface. That means that the electric field is parallel to the area vector. So the cosine would be just 1, and so you could just write it as the electric field times the area is Q inside divided by epsilon naught. But this is the form of Gauss law of electricity. The electric flux is equal to the integral, the closed integral or the closed surface integral of the electric field dot dA, and this is equal to the charge that is inside the surface divided by epsilon naught. If I have some, let's say, some weird shape like this, and I want to know what is the flux through this shape, I could use the symmetry, because I know that the flux that goes out of this surface is exactly the same that goes out of this sphere, if the only charge that is inside is this. Let's say that I don't have any other charge here. So if I want to know the flux through this surface, I could put a Gaussian sphere. The Gaussian surface is usually drawn with dot lines, and so you calculate the Gaussian, the electric flux, and so if you want to know the electric field here, you would put a Gaussian surface here at this point, you will calculate the electric flux here, and you will divide that by the area. Or you could say with this you have so that the electric flux is equal to Q inside divided by the area of the Gaussian surface times epsilon naught. This is for electricity, and the one for magnetism is quite the same. Would be just that the magnetic flux is equal to, here is the open surface, the open integral of the magnetic field dot the area, but this will always be equal to 0 because when we have a magnet, we have a south pole and a north pole. The direction is always in this, from north to south, like this. So whenever I take a part, something like here, the magnetic flux is here is coming, and here is going out. Or here I can put it as here. This is the north pole, this is the south pole, so it's going in this direction. So if I take, for example, this surface, I have that in this part, here it is coming in, and here it is coming out. So always the magnetic flux in this through a magnet is 0. That is because the magnets are always coming like dipoles. But if we have a magnetic monopole, it would be different, but we think that there is no magnetic monopole, so while we don't discover, this is true. These are the two Gauss law, and these are the first two Maxwell equations. And later, this is for electrostatics, and later we will discuss Maxwell equations that has to do with motion, that has to do with magnetic field or electric field generated by the magnetic field or by the electric field, that is by moving charges.